Hello, everyone, and thank you for joining us for this presentation. CLT Stands Up, a look at cross-laminated timber wall design. My name is Michelle Cambiron, and I'll be starting off the presentation first, and then partway through it, we'll have Lori Cook, who will be joining us to provide the presentation on a detailed design example for the cross-laminated timber wall. And this presentation is copyrighted by American Wood Council, included in the PDF that you should have a copy of to follow along while I am presenting. There's the description and learning objectives. We're going to start off with 3 polls to get an idea of the makeup of the audience. And so our first poll is shown here.
All right, so what is your profession? Are you an architect, engineer, code official, fire service, builder, manufacturer, or other? Let's see, we have about 68% engineers, 20% code officials, and 7% builder, manufacturer, or other, 4% architect, and 1% fire service. No matter what your profession, we are so delighted that you are here and hope that you find something of value today.
Great. So let's do the second poll because we're interested in hearing about where you are in the U.S. And if you're outside the U.S., unfortunately, we're limited in poll answers on the options. So perhaps you could type it in the chat if you're outside of the U.S.
Absolutely. And I'm just going to give you just a couple seconds to take a look at this map so that you can designate which color you are. And then I'm going to open it up. Well, this is so interesting to see. We have pretty much an equal distribution across the states. How exciting. So, all right, I'm going to close. 24% in the west, 23% northeast, 20% south central, 18% in southeast, and 15% north central. How exciting. So,
wow, great. Did anybody type in for the chat outside of the U.S.?
Let me
I didn't see anything. So
um,
we'll go ahead and launch the last poll before we start into the presentation, just to get an idea of the experience with our topic of CLT from the audience.
How familiar are you with CLT? Let me launch the poll here. So, are you a guru? Have you designed or plan reviewed many CLT projects and can teach this course? Are you a craftsman? You've designed or plan reviewed many projects with CLT. Are you an apprentice? You're familiar with CLT but have no design review of project experience. Are you a novice? You're just starting to learn about CLT. Or what is CLT? 56% are familiar but have no real experience designing or reviewing. 33% are just starting to learn. So this is the right webinar for you all. 8% are not familiar, and just a tiny little bit of you are craftsmen and gurus. So we are delighted that you are here, and really this is the right webinar for y'all. So
Yes, definitely. Thanks, Marcy. And as Marcy mentioned, this is really a good presentation that will cover all bases of the audience's need. So to give you an overview about the presentation, we're going to start off with CLT building examples for those of you that are not familiar with this type of construction and this type of wood product. Then we'll get into the codes and standards that are applicable for using CLT in your building and plan reviewing and designing. And then finally, we'll end up with Lori Cook taking over the presentation, where she'll be discussing CLT wall structural and fire design and providing step-by-step example. And also, we'll end up with some resources that'll assist you when you're looking at designing or plan reviewing these types of projects. And then let's go from there to the next next slide. So light frame construction, this is something that we're all pretty familiar with if you're designing wood construction. And right here you see some mid-rise projects that are built out of using sawn lumber or engineered wood products. And the ones shown here are built in a platform frame construction, where you would see the wall being built up on the floor and then tilted up, and then on top of the top plates you would have the joists sitting on top of the top plates, and then wood structural panels added to that, and then another wall on top of that. That's what's called platform frame construction. And then this picture on the left actually is a mid-rise construction over a concrete podium. So that's an example of what we are probably used to when we think of wood light frame construction, at least in residential multifamily construction. And then when we look at mass timber construction, mass timber is actually not defined in the code. However, there will be a definition in the 2021 code, which really is a type of construction that has large wood elements made up of cross-laminated timber, nail laminated timber, or in the code it's called mechanically laminated timber or glue laminated timber, that are built up into large elements or panelized construction. This actually, the cross-laminated timber is a panel, comes out as a panel. We'll talk more about that later. But this is an example of a project that was completed in 2009. Now, I actually joined the wood industry in 2008, and cross laminated timber was really a new type of construction in the US, whereas it's been actually been used throughout the UK and other areas of Europe or Australia for quite some time, especially in the UK and France and Europe. And this is an example of a 9-story building, which is 8 stories over one level of concrete podium, mixed use, mostly residential. And it was completed in 2009. Now, at that time, this was the tallest modern timber building in the world, to be exact, of cross laminated timber. And the unique aspect about this project is not only that it utilized cross-laminated timber, but the reasons why it used cross-laminated timber. One is the sustainable aspects of using wood products, and the other is the speed of construction and the noise sensitivity to the site. And in the UK or in Europe or London, there are policies in place that state that for new construction, they have to have a very small carbon footprint. That's one of the things. And there's other things like renewable energy, et cetera, et cetera. It has to be a very sustainable project. Well, when the designers were looking at designing this project, they looked to cross laminated timber because of the sustainable aspects that wood construction has. And for this example, which used 910 cubic meters of cross-laminated timber, the cross-laminated timber is stored up to 186 metric tons of carbon dioxide. Wood, it happens to be 49% carbon dioxide, wood alone. And then because they used wood, they avoided greenhouse gas emissions by 125 metric tons of carbon dioxide, meaning that since they used wood, they avoided greenhouse gas emissions if some other product was used, such as concrete and steel. And then so the total potential carbon benefit for this using cross-laminated timber is 300 metric tons of carbon dioxide, which is equivalent to approximately 65 cars off the road in 1 year. Now, so that's really for the sustainable benefit of using cross-laminated timber. The other benefits I mentioned are the speed of construction for this project. It took 4 carpenters 27 days to erect the wood structure. That's they estimated a timeline reduction of 72 weeks to 49 weeks, that they reduced the timeline in construction quite a bit. And then Also, the weight of cross-laminated timber is approximately 4 times less than what concrete building would have been. So reducing the foundation by 70%, it was estimated. Another benefit of using cross-laminated timber is the site sensitivity to noise. All of these panels were prefabricated off-site, and so when they were trucked to the site, they needed a crane to erect the panels in place. So then there was very little noise than what you would see here on a normal site with using other types of construction. So those are the benefits. And so that was back in 2009. Now, fast forward 8 years, and here we see Brock Commons, which is the tallest mass timber structure in North America. And it's 17 over 1, so that's 18 stories, 17 of wood construction over 1 level of concrete podium. It's a mixed use student housing project, and it was completed in September of 2017. And one importance of significance about this actual project is that if you've heard of the ICC Tall Wood Building Ad Hoc Committee that was formed to look into using mass timber construction to build to taller heights, they utilized the information from this particular project to formulate and help provide information for creating the 14 code changes that were introduced in the 2021 and also approved for the 2021 code. I think Lori will mention something about this later on in the presentation. But this project, as I mentioned, is 17 stories of cross-laminated timber, and it is supported by glue laminated timber columns. And we see that so that's 17 stories across laminated timber. And then the roof is actually made out of prefabricated sections of steel beams and metal deck. But the vertical lateral resisting system is 18 stories of concrete walls, 2 cores that house the stairs, the exit stairs, and the elevators. And so that provides the vertical lateral resisting system. And for the wood construction, it took 70 days to construct the wood construction part, the wood structure of this building. So it went up very fast. And for this structure, it had 2,233 cubic meters of cross-laminated timber and glue laminated timber wood products. And just to give you an analogy about how much wood that is, it would take approximately 6 minutes for US and Canada forests to grow that amount of wood. And that amount of wood stores 1,753 metric tons of carbon dioxide and avoided 678 metric tons of carbon dioxide greenhouse gas emissions by using wood rather than some other building material, with a potential carbon benefit of 2,432 metric tons of carbon dioxide. And that's approximately equivalent to 511 cars off the road in a year. And other projects in North America, this one is in Quebec, Canada. It's called the Abora. When completed, it will be the largest CLT structure or CLT buildings of 3 buildings of approximately 600,000 square feet of mass timber construction. And so it will be the largest when completed, which should be soon. But it's a facility that houses 3 buildings. All 3 are 8 stories high, 7 over 1, 7 stories of CLT structure over 1 level of concrete podium, and all of it is residential structure. There may be some retail on the bottom of these structures. And this is a picture back in 2016, late 2016, of the first building being constructed. And the first building actually only took 7 workers, 76 days to erect the actual wood structure. Right now, I believe building 1 and 2 are completed or near completed, and they're currently working on building 3. There's actually a live webcam that you can Google. Just Google the name, the Abora, and you can see a live webcam of this being constructed. Another project, oh, this is the inside of the building 1 that shows the cross-laminated timber and the glue laminated timber beams that were used for the structure. And another project that is up in Quebec is the Origine, and this is in Quebec, Canada, which is 12 stories over 1 level of concrete podium, and it's all residential construction, and it was completed in 2017. And you can see this is a different type of construction than a platform frame construction. Remember, a platform frame construction typically has one wall, one level wall, 1 story of wall, and then the floor would sit on top of the panel, and then you'd have another panel or wall on top. This one has a panel that goes several stories high, and then the floor would butt against it and connect to the side of the panel. So those are 2 overviews of the type of construction you would see with this mass timber construction. Now, as I mentioned, it's 12 stories of cross-laminated timber over 1 level of concrete podium. And the floors were supported by glue laminated posts and beams. The actual structure was erected in 4 months. And the carbon benefit of this is a total carbon benefit of 3,295 metric tons of carbon dioxide, which is equivalent to about 690 cars taken off the road in 1 year. Now let's move to the United States. Where is mass timber and cross-laminated timber construction going on? Well, here's an example of a project that was completed in 2015. It's the elementary school in Franklin, West Virginia. Now note the date that it was completed. Cross-laminated timber was not adopted into the code until the 2015 IBC. So this was completed using cross-laminated timber prior to it being in the code. And so they had to go through an alternate means and methods to utilize cross-laminated timber. Also notice the headers that are being used here. They're using glue laminated timber for headers, and I'll talk about this later on in the presentation related to this edgewise bending of the panel. So keep that in mind when I talk about this later in the presentation. Here's an example of the first mid-rise hotel in the US. It's the Private Army Hotel in Redstone Arsenal, Huntsville, Alabama. And it was completed in 2016. And although this is showing 3 stories, there is actually 4 stories of construction. And this utilized a platform frame construction where you can see 1 panel and then you see the CLT floor and then another panel in the CLT floor, et cetera, et cetera. And this had, let's see, roughly 58,000 square feet of construction that included studios and suites using cross-laminated timber and developed by Lend-Lease. Now, that was back in 2016, and they also finished their second 4-story hotel in November 2018, and it's an Army hotel, the Candlewood Suites in Fort Drum, New York, all out of cross-laminated timber. And from what I understand, they have quite a few more that they intend to build out of cross-laminated timber. And now bringing it to the Pacific Northwest, where we see a lot of mass timber construction going on, where they're really embracing this type of construction. So much so that they've actually adopted the 14 code changes before it was even adopted into the IBC. And at least the state code adopted it before it was adopted into the IBC. And this is the Albina Yard in Portland, Oregon, that has 4 stories of construction out of cross-laminated timber. And it's an office retail building, which was completed in the summer of 2016. Shows you the interior where they used glue laminated beams and columns to support the cross-laminated timber construction. This project, again, is in Portland, Oregon, and it's carbon 12, which is the tallest mass timber construction in the US currently, and it was completed just recently in 2018. Now, this building was actually a Type 3A construction, which is limited to 5 stories under the code. And since they were going to 8 stories with mass timber construction, they had to go through an alternate means of methods through Section 104.11 in the IBC to introduce to use cross-laminated timber. And 8 stories all out of cross-laminated timber, 85 feet tall. And the vertical lateral resisting system was a core constructed of buckling restraint frames in the middle of the building to provide the vertical lateral resisting system. And so that is the tallest CLT building in the US currently. I'm sure there's more on the boards that we'll see in the near future using cross-laminated timber. And they use glue laminated timber columns and beams to support the panels. Okay, where in the code, or what are the codes and the standards related to using cross-laminated timber? So we'll base this presentation off the 2018 IBC, but it certainly was in the 2015 IBC, and that was the first time it was adopted into the IBC code. And for those of you that aren't quite familiar with cross-laminated timber, this is a close-up look at it. And some people will say it's jumbo plywood, but it has laminations through the depth of the cross-laminated timber. And it's actually been around for quite some time, with the first patent being awarded in France in 1985. And then projects were built in Switzerland and Germany going back to 1993. And through the improvement of press technology and using CNC technology and incorporating it more into buildings so that the industry gets used to using cross-laminated timber, at least in Europe. We have the first multi-story residential construction in 1998 in Austria. And then throughout the 2000s, CLT was significantly increased in use. The main driving factor is the green building movement throughout Europe. And as I mentioned in the example of the Stadthaus project, the first 9-story the tallest CLT building in the world, that was one of the main drivers for using cross-laminated timber. But now there's over 500 CLT buildings in England alone. And as we mentioned in the beginning, it's recently come to the US and Canada, where it's really taking off. So if you're familiar with wood construction, you're probably familiar with engineered wood products, and specifically glue laminated timber, where all the laminations are in the major axis, and the laminations are the individual members that are adhered together are glued together with adhesives. And this happens to be a balanced condition where we see the same grade of lumber top and bottom, and as we get through to the middle, we have lesser grades in the middle where we have less stress, and this acts in beam-like manner along the strong axis. But for cross-laminated timber, each of the layers we have one layer of the laminations in the strong direction, and then the next layer is 90 degrees to that, and so on. So that's why it's called cross-laminated timber. It's a thick orthotropic plate, and that cross-laminated timber, or the cross-lamination, provides some two-way action in that cross-laminated in that panel. Now you see in the long direction where we have the major axis, that's where most likely the laminations are going to be in the long direction, where we're going to need the higher strength, where you have the highest stresses, because it spans in the long direction. And then again, the inner ones are oriented 90 degrees to that. And when we're looking at walls, we can look at it two different types of applications of the loads. Well, there's actually three, but when we're talking about out of plane loading, we would see flatwise bending. So the design properties of out of plane or flatwise loading in CLT is now tabulated in PRG 320, 17, and 18. And I'll talk, that's the manufacturing standard for manufacturing cross-laminated timber. So they're now tabulated, and flatwise bending is bending of CLT under loads applied to the face of the wall in this application, or the face of the floor. And the design properties include ASD bending moments, average bending stiffness, and ASD shear capacity and average shear stiffness. And these in all are tabulated in PRG 320 as a minimum qualification value for both the major and minor strength directions. And these will all need to be verified and obtained from the manufacturer. But note the terminology that I used about ASD, bending moment, et cetera, et cetera. This terminology is not consistent with the NDS, the 2018 NDS in Chapter 10 terminology, which is the chapter on CLT. And the reason is that the PRG 32017 and 18 were developed after the NDS, the 2018 NDS was published. So we will most likely harmonize the language when the 2024 NDS is being developed. So that is flatwise bending, or out of plane loading on the wall, and also loading on the floor, downward loading on the floor, or upward loading on the floor or roof. And then when we're talking about in plane bending, this is properties for in plane edgewise bending. It's going to require qualification testing per PRG 320. And remember when I talked about the header over the openings, where it was infilled with glue laminated timber. And that is because some of the manufacturers have yet to develop their capacities or their design values for their cross-laminated timber. So the loads, the CLT is under loads is applied to the edge, is shown in this figure, in the edge of the panel, and then we have bending around this axis in plane. And it's these values are not tabulated in PRG 320 and must be obtained from the manufacturer. And that's why you will see the supplemental framing in that location, the header location, because there are no tabulated values in PRG 320. And note that the design values and section properties will require both major and minor axis directions. So the terminology, again, that you see here on the slide is different than what you would see in the 2018 NDS. But again, they'll be harmonized when we develop the 2024 NDS. These are some typical panel connections that you would see, typical angles, and these are self-tapping screws or wood screws that you would see a lot. The self-tapping screws are going to be proprietary type fasteners, so you would have to see the manufacturer, and they would probably most likely need to have an ER report or ESR report for the code official to approve them. And here are some typical connections that you might see on a job site where it's using cross-laminated timber, uh, where we have members connecting or abutting. Imagine if this was a wall panel here, and that would be a balloon frame type connect panel, and then the wall, the floor connecting to the wall. Other applications, pretty simple applications or connections. Now, for the panel to panel connection, when they sit side by side, at connecting the edges of the panels together to provide that continuity of load path, there are two typical type of connections because of the ease of constructing these type of connections. One is this single surface spline where the two panels would abut together, and then a spline of plywood or LVL will be used to splice the two members, the two CLT panels together. And of course, the screws would be connecting and continuing that load path from one panel to the other. The other one is using a half lapped connection, and you would see that this does not require extra material other than the self-tapping screw to connect the two panels together. Now, how did it get into the 2015 IBC when it was first adopted into the 2000 IBC? Well, it had to go through the typical process of providing substantial information to substantiate the use of CLT under the code, looking at fire and structure. And American Wood Council did a fire test to show the fire resistance of the panel. And this shows you a test. And also FP Innovations also did some testing. That's a Canadian organization that provided some testing also to help provide information on using cross-laminated timber and the fire resistance. Now, the American Wood Council did an ASTM E119 fire endurance test, which is a test that is mentioned in the code that is used to provide information on how much fire endurance a product, any product that is used in a building that can be tested using this ASTM E119 test or standard test. And this panel had 5 plies of CLT, which is approximately 7 inches, and 5/8 type X gypsum on each side of the panel. And we had a 4x8 panel, two of them side by side with a half lapped splice or half lapped joint in the middle, and connected together with self-tapping screws. The test, they sought to get 2 hours of fire resistance rating, and it actually lasted for about 3 hours and 6 minutes. It was 3 hours, 5 minutes, and 57 seconds, actually. And it had 87,000 pounds of vertical load on the wall, and it surpassed the 2 hours of rating and went as far as 3 hours and 6 minutes, where we saw a structural failure where there was a buckling of the panel. But it certainly did exceed the 2 hours that was sought in the testing. And because of the test and other information that was provided to adopt CLT into the code, it was first adopted in the 2015 IBC as under type 4 construction, where you can see that it includes not only cross-laminated timber for the first time under heavy timber construction, but also structural composite lumber. But it also continues to be in the code in the 2018 code under type 4 construction. Now, type 4 construction, if for those of you that are not familiar with it, is the type of construction that has large wood members. They need to meet a minimum size that are prescribed in the code, and that's on the interior of the building, and the exterior of the building is required to have non-combustible walls that are walls that are made of non-combustible material, such as cold formed steel. But the code does allow fire retardant treated wood to be used in lieu of the non-combustible construction. And then so no additional fire resistance is required for the interior of the building as long as those wood members meet the minimum requirements of the code for heavy timber construction. And there was information in Chapter 6 of the code in the 2015 that provides the minimum sizes that are needed to meet heavy timber construction. Under the 2018 code, that is information has been migrated to Chapter 23, chapter on wood. Chapter 23 is wood. And so here's the table under the 2018 IBC that you would see. Now, under the 2015, this table was this much information in the 2015. Under the 2018, it's been expanded to provide more information to more easily read the requirements of heavy timber construction and the minimum dimensions. Now, in this table, it provides minimum dimensions or nominal dimensions for solid sawn lumber. For example, 6x6 is what we would call for sawn lumber, which is 5.5 inches by 5.5 inches. And then we have glue laminated net sizes. That's the actual size, or the minimum size for the glue laminated net size. And then we also have it for structural composite lumber. Now, new to the 2018 are these two columns, which really state what members, well, first, what the heavy timber structure member is, and then what loads it's supporting. So this information was actually in the body of Chapter 6, where it was mentioning, talks about the minimum sizes for heavy timber construction. But now it just was migrated into the table to make it easier to understand the minimum requirements. And you notice that cross-laminated timber is not in this table, and that's because there are minimum thicknesses that are in the body of the language in Chapter 23, Section 2304 for heavy timber construction. And again, no additional fire resistance is required because of the long history of heavy timber construction and its wood's innate ability to slow down the speed of fire for the wood member. And I'll mention something more about this later on in the presentation. Now, so where can cross-laminated timber be used in the code? Well, certainly, as I mentioned, under Type 4 construction, all elements can actually be constructed out of cross-laminated timber, as long and no additional fire resistance is required for the interior of the building, provided it meets the minimum sizes. So, as I mentioned, the exterior walls for heavy timber construction or Type 4 construction are required to be non-combustible construction, but we are allowed to use fire retardant treated wood, or you can use cross-laminated timber with fire retardant treated plywood on over the cross-laminated timber, or it needs to be protected by gypsum. And then the floors and the roof may be of cross-laminated timber, provided it meets the minimum thickness shown here. And then the interior walls can be cross-laminated timber as long as they're 4 inches thick. And in addition to cross-laminated timber, nail laminated timber, which is another type of wood product or wood construction, can be used in this situation in Type 4 construction. And then Type 3 construction. Typically, you would see Type 3 construction in mid-rise construction, or I've seen it used in restaurants and other types of construction. Well, it can actually be used for other occupancies, but it is typically used for mid-rise construction, where you see 5 stories of wood construction over one level of concrete podium. So for this type of construction, it requires that the exterior walls be of non-combustible material, but the interior of the building elements can be of any material permitted by the code. And the code allows cross-laminated timber. So the interior can be of cross-laminated timber. And let me go back to the other slide, the section related to the exterior walls. Now, it does say that fire retardant treated wood framing and sheathing may be permitted to be used, shall be permitted to be used at the exterior wall assembly of 2-hour rating or less. And so opening up the door for the use of wood and all wood building. And so for type 3 construction, CLT can be used almost everywhere. And specifically on the interior, it can use cross-laminated timber, and the roof can be of cross-laminated timber. And then the exterior walls can be constructed of fire retardant treated wood, provided the exterior walls are the requirement is 2-hour fire resistance or less. And then type 4 construction. Type 5 construction allows any materials permitted in the code. So certainly cross-laminated timber is permitted in the code and can be used in type 5 construction. So anywhere, exterior walls, the floors, the roof, and the interior walls. So we have a poll, and we'll go ahead and launch this poll.
So, which of the following is the tallest mass timber structure in North America? The Stadthaus, the Brock Commons, the Arborer, or the Origin?
Okay. And the key to this poll is that it is North America. So when we talk about North America, Brock Commons is the tallest, and that it's 18 stories tall. Okay. Okay, so the code. In the 2018 IBC, it references the 2018 NDS. And we talked about mass timber construction. Mass timber construction can utilize all of these wood products to create large wood elements. Sawn lumber can be used to create the nail laminated timber. We have structural glue laminated timber, structural composite lumber, and glue laminated timber all can be used in heavy timber construction and other types of construction. So these are the chapters that are applicable to mass timber construction wood products. And Chapter 10 is where we see cross-laminated timber, and that was new under the 2015 NDS, where we have cross-laminated timber. So we have the charging language in Chapter 10, Section 10.1.1 for utilizing engineering design with performance-rated cross-laminated timber. And important to note and to put on your drawings if you're designing cross-laminated timber or using cross-laminated timber is the manufacturing standard, the standard for performance-rated cross-laminated timber, which is the ANSI APA PRG 320. And for the 2018 IBC and 2018 NDS, it references the ANSI APA PRG 320 and 2017. And this is applicable under the current codes to the low and mid-rise buildings using CLT. That would be under type 3, type 4, and type 5 construction, which is permitted under using those types of construction. Now, one thing to note though is if you are going to go taller with your structure, and there is a or a more current standard, which is the APA PRG 320 2018. And this is the one that's referenced in the 2021 code, IBC code. And so this is applicable for types 3, types 4 heavy timber, and types 5 construction. And under the 2021 code, there will be an expansion of heavy timber construction to type 4A, type 4B, and type 4C. So type 4 heavy timber is the traditional heavy timber construction. Type 4A and type 4B and type 4C uh, allow for the use of mass timber construction to go to higher heights than what is currently permitted in the code. And they have various levels of suppression, sprinkler requirements, protection of the mass timber, et cetera, et cetera. So we do have a webinar that will be coming up in June that will go over the code changes that have been adopted and approved in the 2021 code. We had a webinar also last year in 2018, in June 2018, that went over the actual code changes. And the reason we point this out of utilizing the ANSI APA PRG 320 2018 is if you are going to be designing taller mass timber construction using cross-laminated timber, taller than what is currently permitted in the code, you really should use the 2018 version of the PRG 320. And that is because the adhesive requirements to prevent fire regrowth was changed in PRG 320. And that's the standard that was used to develop the CLT panels that were tested successfully in the full-size test when the ad hoc committee was looking at cross-laminated timber and developing the 14 code changes. So again, going to tall or doing mid-rise construction that is currently allowed in the code, ANSI APA PRG 320 2017 is applicable. If you're going higher than that, then specify ANSI APA PRG 320 2018. And as of March, we were told that 4 of the 6 APA CLT manufacturers are manufacturing CLT per the 2018 version. And it looks like the remaining 2 will be manufacturing in July, probably by July 2019. So when we get our cross-laminated timber, we will want to have those panels stamped, similar with other wood products. Here's an example of a stamp that a product marking that you would see that gives you information on who produced or manufactured where it was milled with an identification number, and the CLT thickness or identification, the CLT layup, the approving agency name or logo. This one happens to be APA. And then also the reference product standard. This one is the ANSI APA PRG 320 2017. Additionally, if you are specifying a panel that is unbalanced, now most panels are going to be balanced where you have the same grade of lumber top and bottom, and it's balanced throughout the depth of the CLT panel. But there may be some time where you would specify a panel that is unbalanced layup. And if that is the case, you want to specify that the panel will need to have a stamp on it that stamps it as top, so that when they're erecting this out in the field, they'll know which way is up and down on the panel and hopefully erect it correctly with the stamp top being on the top of the cross-laminated timber. Now the panels come in various thicknesses. The laminations are 5/8 inch to 2 inches thick, and they're made of sawn lumber or structural composite lumber. The maximum thickness is 20 inches maximum, and then the in-service moisture content that is assumed under the NDS and the standards is moisture content, in-service moisture content of 16%. And that's similar to what you would see for glue laminated timber also. So the reference design values, where do we go to get the reference design values? Well, according to the NDS, you would either see the cross-laminated timber manufacturer's literature or obtain it from the code evaluation report. And the APA website is a really helpful website for obtaining information on cross-laminated timbers. And here is the actual link to this one web page, which you will see on the right-hand column. It lists the members that manufacture cross-laminated timber. And then also on the right-hand column are a list of the CLT product reports that will give you some information on each of the individual manufactured CLT products. Here's an example of the CLT products. And one thing to note is that APA does produce product evaluation reports that are shown here, and they went into an agreement with ICC back in 2012 to have reports that are jointly produced with APA and ICC. Now, these are just through APA, but an APA member can have an APA product report or an ICC ESR report or a joint report, as I mentioned. And but I don't think there are very many CLT manufacturers that have that joint report. And mostly they're going to be I-joist or structured composite lumber that have that joint report. Now, just like any other wood products, the cross-laminated timber has its own table for the applicable adjustment factors for cross-laminated timber, depending on whether you're using an ASD ASD or an LRFD design. For ASD, you would use the gray area and all of these applicable adjustment factors, depending on what mode of that you're looking at, if you're looking at bending, tension, shear, etc. And those are consistent with what you would see, as I mentioned, in with other products. This one actually is modeled after the wood structural panels, similar to that. And then we have updated back in 2015 NDS the provisions for connections. This one is chapter 12 to include cross-laminated timber connections. So see that if you're designing your connections. It provides information on fasteners in withdrawal and lateral loads on fasteners, minimum spacing requirements, etc. Now, what about lateral design for cross-laminated timber buildings? Well, for seismic design, there is no response modification coefficient, an R factor that is in ASCE 716. And CLT is just not recognized as a system in table 12.2-1. But there are options, and that is that doing a performance-based design procedure per ASCE 7, demonstrating equivalency to an existing ASCE 7 system such as say brace frame, or buckler brace frame, etc. And then there's other information related to using cross-laminated timber. But the other option is to use a system that's already prescribed in ASCE 7. I showed you the carbon 12 building that had cross-laminated timber floors, and it used buckling restraint frames for its vertical lateral resisting system. So that's certainly an option. I've also seen projects where they used just regular brace frames or used moment frames as the vertical lateral resisting system. As far as in-plane shear for lateral loads, again, there is no R value and currently no seismic R factor, but there's ongoing research and standards development on CLT shear walls. The timing, as we understand it, is that the ASCE 722 would be the earliest that a seismic R factor would be codified. Now, there are provisions for CLT shear walls for wind design that are being developed for the 2021 special design provisions for wind and seismic. They're working on it right now, which will be referenced in the 2021 IBC. But in the interim, lateral design using CLT would have to be approved via an alternate means and methods. And fire design, I mentioned that for heavy timber construction, type 4 construction, as long as the wood members meet the minimum prescribed dimensions in the code, there is no additional fire resistance needed for those wood members. In other words, no additional gypsum is required or no calculated fire resistance. So this is prescribed in the code under section 722, calculated fire resistance. And it states that the calculated fire resistance of exposed wood members and wood decking shall be permitted in accordance with Chapter 16 of ANSI AWC National Design Specifications for Wood Construction. So it specifically mentions Chapter 16. And fire resistance, you'll work with the architect who will let you know how much fire resistance is required for the elements in the building. And you can calculate up to 2 hours of fire resistance for columns, beams, and tension members. This can be done for lumber, glue laminated timber, structural composite lumber, decking, and CLT. And this was true for the 2015 IBC and NDS. And what we're doing is we're calculating the amount of char that is needed to build up the char or a sacrificial layer to provide a certain amount of fire resistance, up to 2 hours. And this is an example of fire performance test that was done that tested a steel beam versus a glue laminated timber beam. And they were both the same amount of strength at the start of the test. And as you can see, that the steel beam probably lost about maybe 60% of its strength, where the glue laminated timber beam lost only about 20% of its strength. So this is an analogous of comparing type 2B construction, which is typically steel or concrete, but 2B meaning not no fire resistance rating required for the steel beam, versus a heavy timber construction, kind of a similar type of comparison. Now what we do is we calculate the amount of char that is built into the member, and it slows down the fire to the amount of time that's required, and then there's an inner zone. So we calculate this char, and it's an effective char, and then we take the net section and calculate the structural capacity for fire design of the wood member. And Lori will go into detail on how to perform this type of calculations for the wall. And as mentioned, it's in Chapter 16, and using nail laminated timber, glue laminated timber, and cross-laminated timber. Those are the members that are typical of mass timber construction. There's an adjustment factor table just for fire design, and this table lists the values of K for various mode capacities to adjust it to an ultimate strength basis. We have a TR10 report that provides more in-depth information, background on the NDS, and has design examples that covers decking, glue laminated timber, and cross-laminated timber, to name a few, and then also provides information on the background, the testing that was performed. Now, this is the equation that will be used for determining the A char, which is the char for when it is exposed to fire. So for cross-laminated timber of laminations of equal thickness, the char depth A char is shown here. And the char rate, which is beta sub n, what is typically used is 1.5 inches per hour is commonly used for cross-laminated timber and other wood products. And the section properties are calculated using standardized equations for the area. So you take the net section, determine your section properties after you know the A effective, which is shown here. Now, A effective is 1.2 times A char. And the NDS uses a nonlinear char rate with a 1.2 increase to account for elevated temperatures in the zone where you have, let me go back to the picture previous to this. So you have an A char and then an A effective that accounts for this elevated temperatures near the cold wood between the heat zone and the cold wood, the 20% increase. We have a handy table that takes into account utilizing a char rate of 1.5 inches per hour, and this is for equal laminations that gives you your effective char. For example, for 1 hour of fire resistance rating and the laminations are 1.5 inches, we need to build into the effective char depth of 1.8 inches into our member. And then there's also a table for other members such as sawn lumber, glue laminated timber, and structural composite lumber shown here. So the important thing to note is that when we're looking at cross-laminated timber or any type of member that we're calculating fire resistance, we want to make sure not only that we build in that char into our member, but we also want to look at the system and make sure that the connections, whatever is supporting that cross-laminated timber or glue laminated timber, that the connection is protected for the same amount of fire resistance as we calculated for the member. So wood connections, including the connectors, fasteners, and portions of the wood member included in the connection design shall be protected by the same amount of fire resistance. And that can be done using either wood, fire-rated gypsum board, or other approved materials to protect the connection. Now, this is a wall, just a graphic of the wall if we have a vertical load, and we will calculate the char depth, and Lori will go through this in more detail, but we're using a stepwise approach where we calculate the char and then determine the net section, which is shown here. And that net section, we have this heat zone and then a 20% increase for the difference at that heated zone area. And then we have a net section. Now, when we look at this, we look at the net section, but we don't take into account the laminations that are in and out of the slide because we don't want to take that into our determining our cross section and use it for calculating our structural capacity, to be a little bit on the conservative side. Let me see here. And so just a graphic to show you the net section shown here. And taking out the laminations going in and out of the slide, and that's our net section. And obviously the neutral axis will shift. Once we have our next section, we would get our capacities from the manufacturer. Now, Lori will be taking a conservative approach and utilizing the capacities from PRG 320. That's just to give an approximation. If you're really designing this, you need to go to the manufacturer with that next section, and they will provide you with the design properties. So we have one more poll that we'll look and launch here.
The following information may be found on a CLT product bark. Is that panel layup, panel thickness, width and length, mill name, grade of laminations, answers A and C. All right, so 88% say answers A and C and just a little bit on the other answers. So Michelle, why don't you let us know what the real answer is?
And the answer is, let's do the animation, A and C. panel layup, and mill name. So the width and length will not be on the product stamp, and you'll have the mill name and not the grade of the individual laminations. So we'll go ahead and hand it over to Lori, who will be doing the step-by-step example of the cross-laminated timber wall.
Thanks, Michelle. So I'm going to take it from here, and we're going to talk about some structural and fire design examples, and then we'll wrap it up with some resources for folks that are looking to learn more. So the first example we're going to go into is a combined bending and axial loading example. So this is going to be for a 10-foot high CLT wall. These loads that you see here are not, they're not Thanks, Michelle. So from here, we're going to be doing some design examples. First, a structural design example, and then we're going to go through a fire example. And then we'll close it out with some resources for folks that are looking for some additional information. So the first example we're going to do today is a 10-foot high CLT wall. You can see the loads that it's supporting here. These loads are not factored. They are just used for this example in conceptual terms. So there's not any factoring or other modification of the loads that's been done here. So we're going to design the wall using the properties from PRG 32018. We do note that the NDS references PRG 32017, but this is the latest, so we're going to use that, PRG 32018. So going into the table in the appendix of PRG 320, we see that we have several options for CLT grades. We're going to use a 3-ply CLT panel that's 4 1/8 inch total thickness and a grade E1 material. And the properties you can see that are listed for that's cross section and grade are listed here. And if we were to go in the table, you can see they're reflected here in the laminations used in the major strength direction. So this is again table A1. Table A2 additionally contains some design values that we are going to be using. So the FBS effective and the EI effective again these are coming from the major strength direction. Now you typically are going to want to obtain the section properties from the CLT manufacturer, but for this example we're using PRG 320 because it's a generic standard. And the allowable capacities for the CLT layups are provided in these tables are for 3, 5, and 7 layers. And these are capacities that are deemed achievable by the committee, but the specific manufacturers may have higher values. So these capacities are derived analytically using the shear analogy model, and then the calculated moment capacities in the major strength direction are further multiplied by a factor of 0.85 for the sake of conservatism. And these have all been validated by testing. The 2019 PRG 320 is still being developed. You're going to see an increase in the shear capacities in that, and that's due to a modification in how the shear capacities are being calculated. So you will notice a difference when the 2019 version of PRG 320 comes out. We also specified that we're using an E1 layup. Now the difference between the E grades and the E layups and the V layups that you see here is that the E grades have machine stress rated lumber in their longitudinal layers and then visually graded number 3 lumber in the transverse layers, whereas the V grades only contain visually graded lumber. So we are using an E1 grade for our example. So now that we've gone through some of the terminology and where that came from, let's go back to our wall check. So let's first check the effective wall compression capacity, and we're going to use the area parallel to grain to resist compression in this example. For our 3-ply CLT example, that's only going to be 2 of the plies, and assuming 1 3/8 inch actual thickness, We see that we have an area of 33 square inches per foot of wall. So our unadjusted compression capacity would be calculated to a little over 59,000 pounds per foot of wall. Our effective and adjusted wall buckling capacity, we need to determine the EI, the bending stiffness, where the reference design values for bending stiffness have not been adjusted to include the effects of shear deformation. The NDS states that the shear component of the total deflection of a CLT element needs to be determined in accordance with principles of engineering mechanics. So one method for designing for these shear deformations is to reduce the effective bending stiffness, which is this EI value, for the effects of shear deformation. We can accomplish that using the EI apparent minimum calculation that we see at the bottom here. So this is from the NDS commentary C10.4.1. So this will satisfy the NDS requirement for that shear adjustment for the deflection. Now we need to take a look at our adjusted compression capacity. So these are going to be our adjusted values. We've calculated our unadjusted values, and now in terms of adjustment for the compression, we have a load duration factor of 1.0, and we can calculate our column buckling resistance, our P sub CE, based on Euler buckling. And then our P sub C star is a reference axial compression parallel to grain multiplied by all of our adjustment factors except C sub P. We calculate this alpha ratio, the ratio of the critical column buckling resistance to the reference compression resistance parallel to grain, and we can use that to calculate C sub P. These equations are an alternate format of the NDS provision equations that are in NDS 3.7.1. So these are in the commentary in C 3.7.1.5. They're the same equations. This is just an alternate format of presenting them. So this alpha may not look familiar to you, but it's just a different way of expressing the existing equations that we have. So back to our calculating our adjusted compression capacity, our P prime sub C, we can calculate that the capacity is a little over 30,600 pounds per foot of wall. Now the adjusted bending capacity is what is resisting the moment due to the applied wind load. So for wind, we have a load duration factor of 1.6. Our moment is simply calculated using principles of engineering mechanics, so WL squared over 8 gives us our applied moment. And then we can calculate our resistance moment using the FB prime S effective times our appropriate adjustment factors. C sub L is equal to 1 in this instance because our depth is less than our B value. So for our 1 foot wide strip of wall, we have a 4 1/8 thick section. So we are able to set C sub L equal to 1, which is our beam stability adjustment factor. So we've shown that the capacity is sufficient in both the axial and bending directions in terms of the individual demand, but we do have to do an interaction check, a combined demand check that compares the capacity in both bending and compression at the same time. So using the combined interaction check, we see that the ratio of these two elements needs to be less than 1.0. So using our handy dandy MathCAD calculation, we see that our combined value is equal to 0.86. So we have met that requirement. It's less than 0.1. The less than 1.0, I'm sorry. So the design process that we're going to talk about next is one that is going to involve a fire design. And the NDS, and we talked about this a little bit in the previous example, the NDS does state that reference design values need to be obtained from the CLT manufacturer or an evaluation service report. And also for fire design, you'll see here in the note here from chapter 16 on the right side of the slide that reduced section properties also need to be provided by the CLT manufacturer. Again, since these are generic examples that we're doing, we're going to use values out of PRG 320, but you would want to make sure you confirm these with your CLT supplier. So our TR10 wall example here, this is a fire design example, and we're going to try to design a load that, or I'm sorry, a wall that will effectively support the axial load. So this one is only going to be supporting compression loads. There's no bending assumed in this specific example. So we have an axial panel capacity, or I'm sorry, an axial panel load based on our pre-specified loads from the example that is in TR10. And we see that this is our panel load, our 20,000 pounds per foot of panel width. Going into PRG 320, section 18, we're going to use a 7-ply CLT panel that's made again from 1 3/8 inch laminations. So our total panel thickness in this example is 9 5/8 inch. And what we want to do is make sure it can adequately support the load that we are applying on it. And also we're going to try to design it for a 2-hour fire resistance. So calculating the effective wall compression capacity, the format is the same as we did in the previous example. We're calculating it based on the area parallel to grain. So in this example, we actually have 4 laminations that are going to resist the load. So we have 66 square inches per foot of width. And we can see that our capacity is 118,800 pounds per foot of width. Next, we need to calculate the wall buckling capacity. So this is again the same as the last example. NDS equation 10.4-1 gives us the EI apparent calculation. We're assuming a pin-pin column buckling condition with the case of S equal to 11.5. So using the EI at min from the NDS commentary and the NDS appendix, we can calculate our adjusted bending stiffness, the apparent bending stiffness for the shear deformations. So we can see that calculated here at the bottom. So now calculating the adjusted allowable column capacity. We'll again use the general form of the Euler buckling equation to determine our P sub C star. And then calculating C sub P. We'll use the same equation format that we used previously. So this is again very similar to what we did in the last example. So we've determined that our 7-ply panel, the capacity of it does exceed the load that that's been applied to it, so that's good. Now we need to go ahead and check for the capacity after 2 hours of fire. So we need to first check the mass loss due to charring, and we're assuming that we have, again, 1 3/8 inch lamination thicknesses and a 2-hour fire resistance that we're calculating for. So we're assuming that we're losing 3.8 inches of section. So that 3.8 inches of char is going to penetrate through the first face lamination, the second lamination, which is a crossing lamination, and then partially into the third laminations. So rather than attempt to account for the relatively small contribution from the remaining portion of that third layer, that crossing strong axis lamination, and also making a conservative assumption that the crossing ply does not contribute significantly to the buckling resistance of the wall, we're going to design what's left of this wall as an eccentrically loaded 3-ply column. So let's look at this illustration to explain that a little further. So again, we said that we're assuming that this first layer is going to be lost to char on the bottom here, and then the second layer is also going to be charred off during our exposure. Our third layer is going to be partially charred, but again, because what's left is not going to contribute very much, we're going to assume that it's not going to provide any contribution. And now our fourth layer here that you see is a crossing layer. And again, in terms of our bearing and buckling resistance, this column is not, or I'm sorry, this layer is not providing very much buckling resistance for our wall. So we're going to go ahead and neglect the contributions of that fourth layer. So now what we have is a 3-ply wall where the neutral axis of that wall has shifted. So the neutral axis has moved, but the load has not. So we need to account for eccentric loading. First, we're going to check the capacity of that remaining section. And again, we're going to assume that we've got a 3-ply panel or something that has similar properties to a 3-ply panel that is remaining. So we go back into PRG 320 and we can pull these section properties from tables A1 and A2 and calculate the wall compression capacity. Again, this is the same thing that we've done in our previous example and in this example. So this is calculating the capacity of what's left after we've lost our layers to char. Same calculation with the apparent wall buckling capacity again, the EI, the buckling stiffness. So we are going to use our adjusted EI parent minimum to determine the necessary buckling characteristics and coefficients. Again, the Euler buckling equation is used to calculate the buckling capacity. P sub C star is our adjusted value with all of our adjustment factors except C sub P. And you'll see that we're using the adjustments for fire. So this 2.58 value comes from the NDS for fire adjustments. So going into our C sub P calculation, again, from the commentary formulas, we check that our fire capacity does exceed the applied load. So we're all right there. Now, remember we talked about that we had an eccentric load, so we have to take into account the moment that is induced by that eccentricity. So the CLT wall is assumed to be loaded concentrically, like we said originally. The one-sided charring would create an eccentricity by the effective char depth. So our eccentricity would be the amount of material that's charred, or the difference between the two sections, so the depth of the 7-ply minus the depth of the 3-ply, divided by 2. So using that 2.75 inches, we can calculate that we've applied a moment. That's our lever arm. Our resisting moment, again, this is a fire design, so our load duration factor, our moisture factor, and temperature are not applicable in this situation. We would only need to apply C sub L, or a beam stability factor, and that's equal to 1.0. So we can calculate our resisting moment due to fire. Again, that 2.85 is our fire modification factor from the NDS Chapter 16. And we see that we have a resisting moment of 12,900 foot-pounds. So calculating our interaction check based on our axial load as well as the moment due to the eccentric loading, we see that we have to, again, have a ratio less than or equal to 1.0. Plugging these numbers into our equation, we see that our interaction ratio is equal to 0.64, and it checks out as being less than 1.0. So again, we made some assumptions in this design that were somewhat conservative, and that simplifying assumption, especially that the remaining cross-section after 2 hours is a 3-ply CLT wall, is conservative, especially in terms of how much time is actually required to char that 4th lamination. So if we go back and calculate the actual time required to char each lamination, we see that it is probably going to take somewhere between 2¼ to 3 hours for this wall to actually char to the point that we've calculated it. So a more rigorous analysis could give us a more precise fire resistance rating, but this is a brief example where we've made some assumptions for the sake of simplicity, and we have shown that indeed our wall does meet a 2-hour resistance rating from a structural standpoint. Now, we do need to take a look at thermal separation that's required by ASTM E119. And this is so that floor assemblies prevent the passing of hot gas from one area to another from penetrating. So the designers could accommodate this through a few different ways. We're going to first calculate the total burn through time, and then the time of separation is equal to that times 0.85. So using the equation in TR10 here, equation 4411, we see that our total burn through time for this section is 562 minutes. Our T sub TS is 0.85 times that, so we get 478 minutes of thermal separation, which does exceed the 120 minutes that we wanted to achieve for this assembly. Other ways that you can accommodate this, some designers will use a floor topping on their CLT floor, such as gypcrete, and that gypcrete can be for multiple things. It can be for, to help prevent sound transmission. It also can help in your thermal resistance. So things like gypcrete toppings can serve multiple purposes in your assembly. We're going to jump into our last poll here.
All right. So, which of the following is true for CLT wall systems? Manufacturer or code ER provide reference design values. The deflection criteria in the IBC is the same as the NDS. Exposed CLT may be designed for 2 hours of fire resistance. All of the above, or answers A and C. All right, so 50% say answers A and C, 48% all of the above, and 2% other. So what say you, Lori?
All right, thank you. And the answer is A and C. So the tricky one on this is answer B. The deflection criteria in the IBC is the same as the NDS. So the NDS actually does not have any deflection criteria in it. We have information on how to calculate the deflection, but the limits on deflection are going to be in the IBC. All right, so now we'll wrap it up with some resources that folks can point to and take a look at. So obviously some great resources if you're interested in learning more are our website and our standards. So if you go to awc.org, we have both print and PDF versions of the National Design Specification, the NDS, the special design provisions for wind and seismic, or SPIDWIZ, you might hear us refer to that as. So there's a 2018 version of the NDS. SPIDWIZ, the most recent version, is 2015. We also have a 2018 version of the Wood Frame Construction Manual. That document isn't really geared towards CLT construction, But if you do residential or 1 and 2 family dwelling construction, that's a really handy document. Some e-courses that we have that might help you if you want to learn a little bit more about CLT or the NDS. We have the 2018 NDS changes, which is course number STD 120. And then we have a CLT design example for CLT as a floor or roof element, which is DES 441-1. Another course we have that relates more to code items, ICC Tallwood Ad Hoc Committee items, is DES 605. And all of these classes can be found on our website at awc.org/education/ecourses, or check out the link on our page. You can take these courses for free, and you'll get free continuing education credit for all of them after you pass a little quiz. And then finally, we have several Structure Magazine articles. You can check them out on our website as well, awc.org, and then click on Publications. We've got articles on the 2018 NDS, 2018 Wood Frame Construction Manual, and 2015 Special Design Provisions for Wind and Seismic, amongst other things. And then that's all I've got to say for today. So I would like to take a break, and we'll take some questions and go from there.
We have such a great audience that they really are on their toes, and I actually misspoke on one of the slides related to the test that was performed by AWC, the ASTM E119 test, and that test actually failed due to the the CLT failed due to the buckling of the CLT panel after 3 hours. However, we did have some other tests that were performed, CLT rooms, where the CLTs remained uncharred under the protected gypsum. So thank you, Mr. Cody, for pointing that out. I appreciate everybody being on their toes and letting us know when we're saying something incorrectly. The other thing I want to point out is where can we get more resources on tallwood mass timber construction? And here's our website, awc.org. On the right hand, we have some quick links that are shown here. And if you click on tall mass timber construction, it has a lot of helpful information related to mass timber, tall wood construction, mass timber. So you can see here it has information on our fire tests that were performed, the 14 code changes that were submitted and approved for the 2021 IBC. Very exciting times. That summarizes the different types of construction shown here. I mentioned that we are expanding the type 4 construction to A, B, and C. So that's a very helpful link. And we are going to have a webinar on the code changes for the 2021 code that were approved, the 14 changes, and that'll be in June. Marcy mentioned that earlier. We also have a lot of webinars on mass timber construction. So a lot of helpful tips shown here. The other thing I wanted to point out is what other resources are available. Now, Marcy mentioned Woodworks, and they have a lot of helpful information on their website. One place that to go to is there's a publication called Tall Wood Buildings in the 2021 IBC, which was co-authored by Woodworks and Dennis Richardson of AWC, which is shown here. Gets into a lot of detail related to the code changes that were submitted and approved. And they also have a really helpful site that shows, let's see here, some building trends. Often we get questions, well, this is pretty new construction. Where is it being built throughout the U.S.? And again, Woodworks website, they have a map that shows buildings that are either in design or constructed in the U.S. And this one's been updated in March 2019. They frequently update this. So some more information. Another question came up related to the fire tests that I showed from the glue laminated timber beam versus the steel beam. And one thing I want to point out is we have a lot of engineers in the audience, and we have some helpful tools and presentations that are really informative about fire resistance and how designers, architects determine the size of the building. And I've also given it in person to a lot of SEA organizations throughout the nation. But when you think about it, when we're determining the type of construction, how involved do structural engineers get in determining the type of construction? And when I ask an audience, very few raise their hand. And so the presentation that we have will help engineers be part of that conversation. So related back to the test, what we see is these are the types of construction, and this table is used for the minimum fire resistance requirements that's required based on type of construction and the structure, protecting the structure. So we have here a type 2B construction that's unprotected. So that would be similar to a steel structure that's not protected, and then compare it to a heavy timber construction. So one could make an analogy that that's what we were comparing, type 2B construction, no protection on that steel beam, versus type 4 construction. And another thing to consider is when you look at the amount of square footage that is allowed, let me go over here. Go to chapter 5, where we look at the type of the sizes of the building. That's height. And again, this is chapter 5. And then we have square footage, minimum square footage, and these are the occupancies here. Type 2 construction, 2B is shown here. That's the square footage. Heavy timber construction provides as much or more square footage, just the baseline, as type 2B construction. Okay, let's see if we have any other additional questions from Buddy. Do you want to ask your questions for specifically?
Yeah, thanks, Michelle. And Lori, good job. We did have a few other questions come in. Lori, a couple for you. One was about floor openings in CLT. Are there any limits on that? Do those need to be supported? What are you thinking?
All right. Floor openings.
Like stair openings, that type of thing. Or even window and door openings.
Yeah,
in the CLT.
So typically so in terms of production, they are going to be cut open. You would have those openings pre-cut at the manufacturing facility. In terms of supports, I do believe, Buddy, I think you could probably correct me if there's some provisions for CLT headers as well. So that is something you could design, but oftentimes the openings would be wouldn't have to be supported, unless the panels were typically thinner. But oftentimes you can design it without additional supports, I think.
Yeah, really comes back to the manufacturer and what they have tested and evaluated, and really, since this is such a new product, you're going to have to be in close touch and discussion with the manufacturer to make sure you're covering all the bases. As you saw in the examples, a lot of the properties have been developed for CLT. Some are still being developed, but there are qualification procedures for all of those in the PRG 320 standards. So Lori's right. If it's coming to the job site and the openings have already been designed, and those openings are already pre-cut into the walls and floors, then you should probably assume but verify that the manufacturer's accounted for that. But if they're making site corrections or site, cuts on the product, modifications, thank you for that word.
Yeah.
Then you really need to touch base with the manufacturer to make sure that those are adequate. Lori, there was also a question about in the example about lamination thicknesses.
Mm-hmm.
Where did that come from? What are the different options there?
That comes out of PRG 320. So I do believe they specify 1 3/8 inch for most of them.
It is, yeah.
I don't
That's
believe
typical for
I don't believe you're limited from using 1.5 inch thickness laminations if a manufacturer is producing with nominal 2x. But I think typically that 1 3/8 inch is the standard.
at least in PRG 320.
Yes.
There's a table in chapter 16. I know it's not intuitive that that's where you'd go, but in the fire design chapter, table 16.2.1b lists some of the various lamination thicknesses for calculating the fire design. It shows a range of from 5/8 of an inch to up to 2 inch thickness, actual thickness for lamination thicknesses. So the other thing too that folks should be aware of, it's not just lumber that can be manufactured into CLT. They're also looking at using structural composite lumber as well. So Michelle, did you have something to add?
Yeah, I was mentioning that on the slide it shows. I didn't know.
Oh, there it is. Yeah, good call. Good call. All right. So Michelle, there were some more questions too about just examples for shear wall design, and there's some discussion about shear walls, but what's your advice about shear wall design going forward?
Well, as an option, well, there's a few things. One is as an option to using a alternate to using CLT shear walls. I think that's what they're asking. What are the options for using CLT shear walls? Under the current code, there are none unless you go through an alternate means and methods. Under the 2021 special design provisions and wind and seismic provisions, the use of cross-laminated timber for wind resistance is being looked at for the 2021 wind and seismic provisions and being balloted now. So that's for wind. For seismic, we're still going to be a ways away for seismic. Part of it is they're doing the research right now. They're going to be determining the R value, and the soonest or the earliest that we think that it will be in the ASCE 7 is ASCE 722. Now, if you don't want to go through the alternate means and methods, you could use a prescribed vertical ladder resisting systems like brace frames, which was shown in one of the previous building examples. Concrete cores, that's used on the Brock Commons, where they use 2 stairwells, elevator concrete cores in the building for their ladder resisting systems. And I've seen moment frames also used for the vertical ladder resisting system.
Great. That's great advice. And regarding the research, I've heard, although I don't know where they are in the exact stage yet for doing this, but I've heard they're going to test a 10-story CLT building, I believe University of San Diego, in the next year or so. And I've heard they're calling it a shake and bake, where they're going to test for seismic and then
test for fire
tests on it. So
right.
A lot of research going on out there, a lot still being developed, but again, as Marcy mentioned, Woodworks is a good option for folks who are getting into these projects, because they do provide free project support. So we'd encourage you to reach out to your local Woodworks rep if you're getting into a project, and they can help you navigate some of these resources as well. Either of you have anything to add? We're at the bottom of the hour, so if not, we'll wrap up and thank everyone for being here, and hope to see you again next month.
Thanks, everybody.